Now let's try to understand and implement the insertion sorting algorithm. So as part of the insertion sorting algorithm, we will basically try to assume that there are two parts of the array in which one part of the array is sorted and the other part of the array is unsorted. And the aim of ours in the implementation is basically try to pick a value from the unsorted part and try to move it onto a appropriate position in the sorted array such that the size of the sorted array increases in each and every step, and in the end, by repeating the same logic, we basically sort the entire array. Okay, so that is the idea behind insertion sorting algorithm. Like I mentioned, as part of the insertion sorting algorithm, basically we will assume that there are two parts of the array in which one part of the array is sorted and the second part of the array is unsorted. Our aim is to pick the each and every value from this unsorted part of the array, and we need to move it onto the sorted part of the array such that the size of the sorted part will increase. By repeating the same logic, the entire array is sorted. So that is the principle behind insertion sorting algorithm. Insertion sorting algorithm also one of the in-place sorting algorithm only. Okay, so that is something that you have to remember. That means that whatever the array values that we get in the same array, we will try to compare and adjust, and we will try to do all the necessary implementation for getting the sorted array in the input array that we get itself. Okay, let's just try to understand whatever the definition that I have given for insertion sorting algorithm on an example array that we have here. So right now the values that we have in the array are 1, 4, -5, 3, 7 and -2. Now our aim is to sort these values in the ascending order. Okay, so whatever the logic that I'm explaining here, whatever the implementation that I do when I implement this insertion sorting algorithm, the necessary comparisons whatever we are doing between the elements, if you just change that comparison operation, basically you will have a insertion sorting algorithm which will sort the array in the descending order. Okay, but anyway, the values that we have here are 0, 1, 2, 3, 4, 5 are the indexes. Totally we have array containing 6 values in it. Now as part of the definition, I mentioned that we will assume that there are two parts of the array, right? One part is sorted array and the other part is unsorted array. If you observe the array here, how will we able to identify these two parts, right? Because we have an unsorted array in the beginning. But if you carefully observe the array of values that we have here, you will be able to find the unsorted part of the array and sorted part of the array. So which part of the array we consider as a sorted part of the array? That is the big question that we have in the beginning. If you see here, right, if we consider the part of the array where we have only one element, that means that the value at index 0 itself we assume as a sorted part. Anyway, it has only one value. Anyway, the array part in which it has only one value, it itself is sorted, right? So we can consider the element at index 0, that means that element till index 0 we assume it as sorted part, and the values from index 1 till the very last index that we have, we will assume it as unsorted part. Now our aim is to find the each and every value from this unsorted part, and we need to move it onto appropriate position in the sorted path. By moving so, we will basically increase the size of the sorted part. Now let's just try to understand how we will do that. So sorted part is available till index 0. We need to move the values from index 1 till 5 into sorted part. So for that, what I will do is I will pick the value 4. That means the value at index 1. Now basically the sorted part is available till index 0, right? So I will compare each and every value. That means 4 gets compared with all the sorted part values we have. Here we only have one value, right? That means that 1 gets compared with 4. Obviously 1 is smaller than 4, right? That's why there is no swapping involved. As a result, the resulting array will be 1, 4, -5, 3, 7 and -2. If you observe here, first two elements are sorted and the next four elements are unsorted. That's the reason why if you see in the previous step, the sorted part has only one value, but right now in the sorted part we have two values. By doing the insertion sorting once, that means that picking up the value from unsorted array and moving it into appropriate position in the sorted part, we've achieved we've basically increased the size of the sorted part of the array. The next element that we need to move into sorted part is -5, and it is available at index 2, 3, 4, 5, 0, 1. Right now the value -5 gets compared with 4. So obviously -5 is smaller than 4, right? So what we will do is we will move 4 to index 2. The resulting array will be 1, 4, 4, 3, 7 and -2. Remember here we have not yet found the perfect position for value -5. Whatever the index 1 we have could be the appropriate value, but there are still unprocessed elements that needs to be compared and adjusted if required. That's why what we will do is -5 we will store it in some variable so that if we swap we will not lose the track of that variable. And the next value that needs to be compared is available at index 0. So -5 gets compared with 1. Obviously 1 is greater than -5. As a result, what we will do is we will swap once again. As a result, the resulting array will be 1, 1, 4, 3, 7 and -2. Now there are no more elements that we can compare because we are already at index 0. As a result, the appropriate position for -5 is index 0. So we will move it there. So the resulting array will be -5, 1, 4, 3, 7 and -2. Right now if you look at here, 3 values are there in the sorted part of the array and 3 values are there in the unsorted part of the array. Now we need to move 3 into sorted part of the array. So 3 we will store it in some variable. Right now 3 gets compared with the value 4. So obviously 4 is greater than 3. That means that 3 should be somewhere before 4. That's why we will swap. As a result, the resulting array will be -5, 1, 4, 4, 7 and -2. Again the value 3 gets compared with the next value, which is nothing but the value at index 1, which is nothing but 1. As a result, 1 is obviously smaller than 3, right? That means that all the values before 1 are also smaller than 1. So there is no point of going further and comparing anymore. As a result, the perfect position for this is index 2. So we will move the value of 3 to index 2. As a result, the resulting array is -5, 1, 3, 4, 7, -2. Here in the sorted part of the array we have 4 values and unsorted part of the array has 2 values. Now we need to move 7 into its perfect position. For that 7 we will store it in some variable and the indexes also we will store it in some variable. I will show you at the time of implementation, but for now let's just try to understand the logic behind this implementation. So 7 gets compared with the value of 4. Obviously 4 is smaller than 7, right? And all the values before 4 are anyway smaller than 4 only. So there is no point of going and comparing further. As a result, 7 is already available in its perfect position. So the resulting array after this is -5, 1, 3, 4, 7, -2. Right now in the sorted part of the array we have 5 values and unsorted part of the array has only 1 value. Now we need to move this -2 into sorted part of the array. So -2 we will store it in some variable so that we will not lose track of it when we swap the values. -2 gets compared with 7. Obviously 7 is greater than -2, so -2 should come before 7. As a result, we will basically swap it. As a result, the resulting array will be -5, 1, 3, 4, 7 and 7. Remember that we have not yet found the appropriate position for -2. As a result, we only moved the value of 7 to the last position. Okay. Now what we will do, this -2 again gets compared with 4. Obviously -2 is smaller than 4, right? So 4 we will move on to the 7 whatever we had previously. That's why the resulting array will be -5, 1, 3, 4, 4, 7. Okay, now again this -2 gets compared with 3. 3 is greater than -2, so we will swap. Once again we will move the 3 to the next position. As a result, -5, 1, 3, 3, 4, 7. Now again -2 gets compared with 1. Obviously 1 is greater than -2, so -2 should come before 1. So we will move 3 to the next index. The resulting array will be -5, 1, 1, 3, 4, 7. Now this -2 gets compared with -5. Obviously -5 is smaller than -2, right? As a result, the appropriate value for this is index 1. So we will move in -2 to index 1. So the resulting array is -5, -2, 1, 3, 4, 7. So right now the sorted array has a size of 6. That basically means that we have moved all the values from unsorted part of the array to sorted part of the array. Okay, so that is the step-by-step process that we follow for sorting the array using the insertion sorting algorithm. What exactly we did? We basically assumed that elements till index 0 are sorted part of the array and unsorted part of the array are available from index 1 till the very last index we have in the array, and we went to each and every element and we tried comparing it with the values we have in the sorted part of the array to find the appropriate position. We shifted each and every element by one side till we find the particular perfect position. After that we moved the value to the particular perfect position, thus increasing the size of the sorted part of the array. By repeating the same logic, in the end we were able to get the entire array sorted in the ascending order. Okay, so that is the step-by-step process that we follow for implementing the insertion sorting algorithm. Now that we have seen the step-by-step process for performing the insertion sorting algorithm, let's try to write the pseudocode of it and let's just move on to validating the same thing. So here, as part of the insertion sorting algorithm, we will write one function called insertion sorting, and this function will take array of values that needs to be sorted. Okay, after that, just like any other sorting algorithm, immediately we will try to calculate the length of the array such that we can use that length while writing the iteration logic. Now as part of the insertion sorting, we will assume the sorted part of the array is available till index 0, right? That means that we need to run the logic of insertion sorting from index 1 till the very last index we have in the array. As a result, whatever the iteration logic that we will do for picking up the value from the unsorted part of the array, it will basically start from index 1 and it will go on to till the very last index we have in the array. That means that it will go to n-1th index, and in each and every step we need to pick the next value from the unsorted part of the array. That's why I'm incrementing it by 1. Now once we pick that value, we need to find its perfect position in the sorted part of the array, right? That means first of all, whatever the element that we have picked from the ith index, it itself could be the perfect position. That's the reason why what we will do is we will keep track of two variables in this insertion sorting algorithm, which is nothing but, let's just say they are nothing but current index. The current index, let's just define it with I, and the value, let's just name it as current value, or these variable names might change when I implement it. Based on the context, I will try to name the variables, but at this point of time, let's just assume the index is current index and the value is nothing but current value, which is available at ith index. Okay, now we need to compare this current value with the values that we have in the sorted part of the array. For comparing, right, we don't know how many values we have in the sorted part of the array, right? For that, we will again write one more loop. As long as this, whatever the current index that we have, if it is greater than 0, along with this, whatever the current value that we have, if it is less than the value at the current index minus 1th position, because we are comparing from the last value we have on the sorted part of the array, right? The current position is available at ith index, and the latest value in the sorted part of the array is available at I minus 1th index. That's the reason why we are comparing it with, if at all the current value that we need to move on to sorted part of the array, is it less than the value we have prior to the current index where we are at. If at all, if this is the case, what we will do, we will basically move that value to the current index position. That means that array of current index is equal to, we need to move the value at current index minus 1th position. So array of current index minus 1. Now by moving this value, we are not done yet. We need to again compare with the remaining values, and we have to move all the unappropriate values to right side by 1 position. Then we need to move the current value to its perfect position. Now that we have moved the value that is available at current index minus 1th position to the current index, the position for the current value could be current index minus 1th position. That's the reason why we will update this current index variable with current index minus 1. Okay, now as long as we run this loop, as long as we find the values which are greater than whatever the value we have in the current value, we would basically shift by 1 position to the right, thus by increasing the size of the sorted array. Once we fail this while loop, right, we basically found the perfect position for the current value inside this current index variable. As a result, we will simply update the current index value with current value we are keeping track. Okay, in that way we are basically increasing the size of the sorted part of the array. Technically we are simply picking up the value from unsorted part of the array. To find the appropriate position, we are comparing it with each and every value we have in the sorted part of the array. If at all the values that are there on the sorted part of the array in each and every comparison are greater, then we are shifting them by 1 position. And once we shift, right, whatever the index that we are having, that could be the perfect position. That's why we are keeping track that inside this current index variable. Once we fail to satisfy this while loop, we will break out of the loop. As a result, the perfect position for the current value is available inside the current index. As a result, we are updating that current value into current index position. Okay, so that's the pseudocode of insertion sorting algorithm. Okay, now let's try to understand the time complexity and space complexity involved in this insertion sorting algorithm, and that also let's talk in terms of best case scenario and in the worst case scenario. Like any of the sorting algorithms that we are seeing, right, the best case scenario is occurring when we have only one value in the array. Similarly here also the best case scenario will occur when we have only one value in the array. Obviously in that case, whatever the loops that we are writing here will basically get executed only once. As a result, the best case time complexity will be order of 1. And to calculate the worst case scenario, let's just assume that whatever the array that we are getting is having n number of values in it. As a result, whatever the outer loop that we are writing, it is getting executed from index 1 till the very last index we have in the array. That means that it is basically running for n minus 1 number of times. And internally, whatever the variable declarations and all we are doing, right, basically they take constant amount of time only. And the next major logic is whatever the inner while loop that we have. So in the worst case, let's just assume that whatever the array that we have, it could have n number of values, right? Out of all those n number of values, we are worried about the moving the last value we have in the array to its perfect position. So here we basically have n minus 1 number of values in the sorted part of the array, and the remaining one value we are trying to move it onto sorted part of the array. So in the worst case, we could basically run this loop for n minus 1 number of times so that the value could be moved to index 0, because whatever the last value we have could be the smallest value we have in the array. That means that it should be moving to index 0. That means whatever the inner while loop that we have here might be running for n minus 1 number of times. As a result, in the worst case scenario, n minus 1 into n minus 1, which is nothing but after simplification, it will be n square. By using the big O notation, we will say it as order of n square. That is the time complexity analysis of insertion sorting in the best case and in the worst case. To talk about the space complexity of the same thing, anyway, like I mentioned, insertion sorting algorithm is also one of the in-place sorting algorithm only. And here if you see, if you calculate the memory based on the programming language that you're implementing according to the definitions that I have given, right? If you see and calculate, in both cases the space complexity will be constant only. And anyway, insertion sorting is anyway one of the in-place sorting algorithm as well, right? But anyway, that has nothing to do, but based on the way we are going to implement, it is going to take constant amount of memory only in both best and worst case scenarios. Okay, so that is the time and space complexity analysis of insertion sorting algorithm. That basically wraps up the insertion sorting algorithm. In the next video, let's just move on to the divide and conquer based sorting algorithms, out of which the first divide and conquer based sorting algorithm is merge sorting algorithm. That is what we will be discussing in the next video.